Well, I made them bigger. That way you had room for problems. The first couple, we don't need a whole lot of workspace, so I didn't leave those. All right, we are going to talk about a couple main concepts in this chapter that leads us into our next one. So it kind of focuses on energy in this chapter, and that will lead us into momentum. Okay, both of these concepts are considered conserved. So when I say they're conserved, what does that mean? The law of conservation of mass says that mass is not created or destroyed. Good. That conservation concept applies to energy and momentum and mass, right? Energy is never created or destroyed, right? Momentum is never created or destroyed. So what happens if we don't create it or destroy it? What has to happen to it? It has to what? Yep, redirected. It has to transform, right? It just changes form in some way. Okay, so let's walk through energy transformations, just the most basic ones that we know of. Okay, I want you to think about a lamp. What has to happen first before anything can happen? I have to plug it in. So what type of energy is that? Electrical. What happens when I turn it on? We have light energy. Okay, so we go from electrical energy to light energy. What happens if I leave it on too long?
Thermal energy.
It becomes hot, right? And I have heat energy, right? Though that's not energy coming from nowhere. It's just a transformation, right? So we go from electrical to light to heat, all within a span of an hour, right? Or it can happen really quickly or really, really slowly, right? But there's all that sort of stuff that happens every day, okay? So to introduce energy, we're going to look at a concept called work, okay? Work in the physics world means something different than what we use that word as day to day, right? When we say work, it means we think we are doing something, right? We are, we're lifting something, we're pushing something, and that could apply in physics, but there's also situations in physics where you feel like you're working really hard, but you might not technically be doing any work, right? And so we're going to look at what that means. Work is the product of the magnitude of displacement times the component of the force parallel to the displacement. That's a lot of words, isn't it?
Yeah.
Right? It's essentially force times the displacement. Force applied that causes an object to displace. Okay? But the important part of this is if my displacement is horizontal, my force also needs to be horizontal. So when we say force parallel, we're not talking about, remember back when we did inclined planes and we calculated the parallel force, right? That's not exactly what we're talking about here. When we say a parallel force, it just means that the force that's causing the object to move, we only want the force that is parallel to the displacement. Okay, so let me say this again. If my object is going to move horizontally, I'm only concerned with the horizontal component of that force. Okay, the force and the displacement need to be parallel to one another. So that means in order for work to be done, a force has to be applied and an object needs to be displaced. Okay, so no matter how much I push on this wall, am I doing any work? No, why not? It's not moving, right? I'm applying a force. It feels like I'm working really hard, but it's not moving. Okay, the same thing would be here. If I try to lift this table up, right, I can, don't worry, I'm strong enough. But if I try and I don't, what happens? No work, right? It feels like I'm working hard, but I'm not, okay? So that equation I think should go on your equation sheet. I would put this under the category of work and energy. This basic equation here for work, parallel force times the displacement, okay? Or force times displacement. That's the most basic definition for work that we have, okay? A force that displaces an object causes work to be done. All right, so if I'm looking at this drawing, this diagram, okay, what's happening here is I'm applying a force, right? I'm dragging something behind me. Okay, so when I'm dragging something behind me, my force is applied at this angle. But my displacement of the object being dragged is only horizontal, which means I only want the horizontal component of that force. Are we clear with that? Right? The force and the displacement need to be parallel. If I use my applied force here, they would no longer be parallel. So I have to find the component of that is parallel. If my object were being lifted, right, if my displacement was vertical, then what component of my force would I want? Right? The vertical one, okay? So you just have to pay attention to how your diagram is drawn, how your situation lays out, right? What your problem calls for, okay? So it says in this case, the displacement is east, so we're only going to use the cosine of that force, right? Or the horizontal component. Everyone feel good about force components? We're vector experts? Yeah. With gusto, I think, right? Okay. You don't know what gusto means?
No.
Like confidence. Yeah, whatever.
Sounds like Shakespeare.
I'm such a Shakespeare. All right, so let's look at this one. If I pushed a loaded grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart, how much work would be done? Is it as easy as it seems? It is. It is. Okay? Because it says I'm moving my cart 50 meters. Do you think my motion is horizontal or vertical?
It's vertical.
My jumping cart? I think it's horizontal, right? Horizontal. And it says I'm exerting a horizontal force, which means it's just going to be 1,500. Okay? What about the units for work? Okay, it would be this. Work is equal to, I took meters times newtons, or Newton times meters, okay? But we have a shortcut unit for that, or a derived unit for that called joules.
Oh, dang it, I
Should have known that. Energy and work are all measured in joules, okay? We've seen that before in chemistry, maybe, okay?
Where's that at?
Yeah.
Do we have to write that, or is it all?
I think I took out that slide because it was not worth printing. Okay? So 1 joule is equal to 1 Newton meter. All right, I want you to turn to the person next to you or find someone next to you and answer these next 2 questions. Can a force be exerted on an object yet no work be done? That's question number 1. What work is done on an object that's carried as you walk at constant velocity? Okay, I want you to answer those 2 questions with the person next to you. I'm going to give you about 1 minute. Yeah, look at this. What is this diagram called? No, not a motion diagram. From our forces chapter, what's it called? There you go, Oni. Free body diagram. A free body diagram, right, is a force diagram. So, let's start looking at this. Let's go all the way back to our forces chapter. What's this downward force called?
Gravity.
FG, right? What's this one called?
Force normal.
Normal force. Very nice. This one is friction. And then we called this force applied. Okay? And so it says I've got a constant force of 100 newtons. So my force applied is 100 newtons. My frictional force, it said, is 50 newtons. My angle, it says, applied is 37 degrees. Okay? We always assume, unless it says differently, that angle is applied from the horizontal. So do I need to bother solving for F applied Y? I don't. No. So I do need to have, I do need to have F applied X. Why do we need to have F applied X? I have friction, but where's my object moving? Is it moving at this angle? Could I use 100 and move it at this angle? No, it's moving horizontally. Okay? So that means I need to calculate my net horizontal force so that I can calculate work, right? So my net force would be what? How would I set up my net force equation here?
Cosine. That'd be X minus F.
Yeah, force applied X minus friction, right? It's positive forces minus negative forces. Positive forces minus negative forces. Okay? I don't know my net force, so I'm going to keep that there. I need to calculate F applied X. Okay, so yeah, Hannah, what would I use for F applied X? Cosine. F applied X would be 100 cosine 37. We need to make sure our calculator's in what? No, stop. Degrees.
Exactly right.
We don't deal with radians or fractions in here.
I
Okay?
don't even know. Michelle hates decimals.
Fractions are the worst. Okay, 100 cosine 37. I got about 79.9. Okay, so if you didn't get that, you need to check to make sure you're not in radians, right? We want to be in degrees. So that's my applied X, 79.9, minus my frictional force, which means my net force would come out to be 29.9 newtons. Did I do that math right?
Yeah.
Okay. But that's not work, right? That's the net force. And so if I want to find the work done by the crate, what would I do?
Multiply it by 50.
Multiply it by,
40.
right? My displacement is 40 meters. So work is force times displacement. So my work value is net force, 29.9 times 40 meters equals 1,196 joules.
So then why do I have to wait?
I don't know.
Just to mess you up.
So here's another option. Another option would be for me to calculate the work done by friction, the work done by my applied force, and then subtract that. But those are just extra steps, right? Because I would have to take each of them times 40 and then do the subtraction. So the easier way to do it, if it just asks you for the overall work, would be to find the net force first and then calculate it there. Why did I not find the net vertical force, right? Because I could have calculated the net vertical force, but why didn't I?
You didn't need it.
I didn't need it. I wasn't moving vertically, so there was no reason for me to have that net vertical force. Okay? Just a little side step here. If my object is only moving horizontally, what is my net vertical force? 0, right? It's 0, right? It's only moving horizontally, so I don't have any vertical acceleration. So my net force in the vertical direction would have been 0. Is that ringing bells? A little bit?
Yeah.
A little. Okay. All right, let's try this one. Determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill a height of 10 meters at constant velocity, okay? So I only want to know the work done by the hiker. The work done by the hiker, not the net, just the work done by the hiker. So this is a problem where it's asking us to break it into parts, okay? So let's envision here, we've got the backpack on the hiker. Gravity's pulling it down. The hiker's having to apply a force, whether they really feel it or not, right, on their shoulders to keep it upright, okay? So how can I solve for the work done by the hiker? Think about the backpack on his back. Is it individually accelerating? No. And so if it's not moving, right, he's moving. But if the backpack's not moving on his back, what's the net force of my system here? Or what has to be true about these two forces? They have to be congruent, right? The backpack itself is not accelerating, right? He's the one that's causing that acceleration. So if the backpack's not moving, we know that these two forces are congruent. And so I'm able to calculate the force of the hiker just by calculating the force of gravity, right? I'll take Fg equals 15 times 9.8. Let's see. That gives me a value of 147 newtons. Okay? And then my object is moving up a hill. So are my force and my displacement parallel in this case? Yeah, right? Here's the thing about work and about energy is that we don't care how he gets up the hill. He could ride an escalator up the hill for all we care, right? But the backpack itself is going from the bottom to the top, right? So work has been done. So it doesn't matter. It's not what's called a path function. A path function would mean that we're concerned about the steps to get there. But work is not that. Work is just a start and an ending function. We don't care about the path it takes. He can take breaks. He can go as slow as he wants to, right? But the work that's done from the bottom to the top is the same regardless of how he gets there. So the work done by the hiker would be 147 times 10. Okay? It doesn't even tell us how steep the hill is. It doesn't tell us anything about that. It's just that the hill is 10 meters tall, right? A vertical height was changed by 10 meters. So 1,470, what's the unit? Joules. Okay? Now, the next slide asks us to calculate the work done by gravity. What would it be? No, the work done by gravity. is still the same. It's exactly the same, right? Because we already established the fact that the net force is 0. And we said our force of the hiker and force of gravity was the same. So if that's the case, my force of gravity is still 147. And that would mean that my work is 147 times 10, right? 1470 joules. Okay? And so now if I ask the question, what is my net work done? What would it be? What's my net work? Right? Didn't we say our net force on our object was 0?
Is that because they're the same?
Yeah, because it's because my backpack's not accelerating. Right, yeah, okay, there. Our net work is 0 because our net force is 0, right? Our backpack wasn't accelerating. So this is a really long approach to get to our final answer, right? Not an approach I would usually recommend, but we can break it down by individual forces, right? The hiker had to do 1470 joules worth of work to offset the 1470 joules worth of work that gravity was doing so that the backpack stayed in place, right? That's essentially what we worked through there, right? The hiker had to do enough work to offset gravity, so he's not falling down the hill from his backpack, right? He's got to do enough work to carry it up, right? But it's the overall system had no work done, okay? Electrical, heat, thermal, all those different types of energy. But we're going to talk about what's called kinetic and potential energy. These are the two main categories of energy, kinetic and potential. Do you know what these terms mean? Kinetic and potential? What's kina? What's the prefix kina mean? Movement or motion, right? So kinetic energy is energy of an object that's in motion. And potential energy is the energy that is stored, right? What it has the potential to do. So stored energy is called potential energy. Okay? The overall kind of definition for energy is the ability of an object to do work. The ability of an object. So does an object have the ability to apply a force and displace something else? Right? Does it have an ability to fall on an object and displace it? Does it have the ability to push an object and displace it? What does it have the capabilities of doing? Right? The ability of an object to do work. Okay? So we're going to start with kinetic energy. We said it's the energy of motion. Okay? Kinetic energy is transferable. That's really one of a concept that we see in real life a lot is the transfer of kinetic energy. Okay? When one object exerts a force on another, the second object is moved a certain distance, then we see that work has been done, right? If something hits another object and causes that object to move, we've transferred kinetic energy, which means that work has been done. So these two concepts are really intertwined, right? Kinetic energy and work really have a lot to do with one another, okay? A transfer in kinetic energy usually causes work to have been done, okay? So here's our equation for kinetic energy. What do you think the M and the V probably stand for? Mass and velocity. Good. 1/2 mv squared. Mass and velocity squared. Okay. Energy is also measured in joules. So both work and energy are measured in joules. Okay. All right, since we know that work and kinetic energy are intertwined, right, because a transfer of kinetic energy will cause an object to move, right, a collision like that will cause an object to move, we're going to look at how they are connected, okay? Work is equal to, what's that mean? Change in, or delta, right? The net work on a system is equal to the change in kinetic energy. So if the work done is 500 joules, that means that our object had a kinetic energy change of 500 joules, right? It means that energy was added or taken away, but our net work is equal to the change in kinetic energy. So you can write it down as delta, or you can write it down as final minus initial, whatever you prefer, but I would probably put this one on your equation sheet as well, okay? The only thing I want to make sure that we see here is that for this equation to work, we have to be looking at the net work, not the work done by friction or the work done by an applied force. We have to look at the net work. Okay? I want you to grab your calculators out because we're going to try a couple practice problems with kinetic energy, and then we're going to call it a day. Okay, so I want to try a couple with kinetic energy. Okay, a baseball's thrown with a speed of 25 meters per second. What's its kinetic energy? How much work was done to make it reach this speed if it started from rest? Okay, so it asks us two different questions. What is our kinetic energy when it's moving 25 meters per second? And then how much work was done to make it get there? Okay, do you see any red flags right away?
Grams.
Yes, grams. What should it be in?
Should be grams.
Always kilograms, right? Always kilograms. So if I want to solve for the kinetic energy, if I want to solve for the kinetic energy, I would say 1/2 m times v squared. And I get a value of around 45.3 joules. Is that what you had?
Yep.
So if I'm trying to calculate, is everyone good on calculators there? Fine with that calculation? 25 squared. I converted this from grams to kilograms. Yes or no?
Yes.
Okay. So now if I'm trying to solve for work, I said that work is equal to delta kinetic energy. Now, is this the initial kinetic energy or the final? Final, because it tells me here that it started from rest, right? Really important to make sure we pick up those context clues in our problem. So if work is equal to the change in, I would take 45.3 minus the initial kinetic energy, which has to be 0, right? When an object is at rest, does it have any kinetic energy? No, it can't, right? Number one, it's the energy of objects in motion. But number two, my velocity would be 0. And anything times 0 is 0, right? So there's no way that I could have any kinetic energy there. So in this case, my work and my final kinetic energy were equal to one another. Okay? All right, let's look at the next one here. Why don't you try this one on your own? I'm going to give you a head start on the next one. How much work is required to accelerate a 1,000-kilogram car from 20 meters per second to 30 meters per second? Okay? So you're going to have to plug in both of those values to be able to figure out how much work was done. Is that similar to what you had?
Yes.
Okay, it's really important here. When we're working through this problem, it's so easy to just put this one in first and this one in second, right? Because that's the order they come in the problem. But we've got to make sure that we're thinking about context clues, right? Initial and final. But in our problem, it needs to go final minus initial. I'll see that a lot, okay? Mathematically, you need to make sure we do the square first before we do the subtraction, right? Sometimes we try to distribute or pull that out. I don't know what that's called. Factor that out, right? Bring those out in front and then do 30 minus 20 squared, but that's not the same as 30 squared minus 20 squared, right? So make sure we do that part first in our algebra step. Okay? Comfortable with that? Okay. We're going to stop there with notes for